This is going to be the lecture over sections 30.8 and 30.9. So for each type of massive particle, electron, proton, neutron, there exists an antiparticle. When the particle and the antiparticle collide, they can annihilate. Protons and neutrons, as well as hadrons, are made of quarks of fractional charge. The proton consists of three quarks, an up and up and a down, while the neutron is made of an up and a down and a down. Mesons are made of quarks, combining a quark and antiquark, as in the pi plus meson. And the world we encounter every day is numerous substances with varying properties. While the properties are many, the fundamental building blocks are few: up quarks, down quarks, electrons, and photons. So it can be argued that the study of fundamental particles began about 400 BCE, when the Greek philosophers Democritus and Leucippus, yeah, that's it, suggested that matter is made of indivisible particles that they call atoms. In other words, you can divide things down to a certain level. And that idea lay dormant until about 1804, when John Dalton, also called the father of modern chemistry, discovered that many chemical phenomena could be explained on the basis of atoms of each element as the fundamental indivisible building blocks of matter. Towards the end of the 19th century, it became clear that atoms are not indivisible. The electron, the photon, and the proton were all discovered within a span of about 20 years at the beginning of the 20th century. By 1925, quantum mechanics was in full flower as the key to understanding atomic structure, although many details remain to be worked out. And at that time, it appeared that the proton and the electron were the basic building blocks of all matter. So the discovery of the neutron in 1930 was an important milestone. And then Walter Both and Herbert Becker observed that when beryllium, boron, or lithium were bombarded with high energy alpha particles from the radioactive element polonium, the bombarded material emitted a radiation that had much greater penetrating ability than the original alpha particles. And then experiments by Chadwick the following year showed that this emanation consisted of uncharged electrically neutral particles with mass approximately equal to that of the proton. Chadwick christened these particles neutrons. A typical reaction using a beryllium target would produce the reaction that you see here, including a neutron. Because neutrons have no charge, they produce no ionization when they pass through gases and are not deflected by electric or magnetic fields. They interact only with nuclei and can be slowed down during elastic scattering with a nucleus, and they can penetrate the nucleus. Slow neutrons can be detected by means of other nuclear reaction, the ejection of an alpha particle from a boron nucleus, according to this reaction. And because of its electric charge, the ejected alpha particle is easy to detect with a Geiger counter or other particle detector. The discovery of a neutron cleared up the mystery about the composition of the nucleus. Before 1930, it had been thought that the total mass of a nucleus was due only to its protons. Nobody understood why the charge to mass ratio wasn't the same for all nuclei. It soon became clear that all nuclei except for hydrogen contain both protons and neutrons. In fact, the proton, the neutron, the electron are the basic building blocks of atoms. One might think that would be the end of the story, but no, you've got more stuff coming. Positive electron, or positron, was first observed in 1932 by Carl Anderson during an investigation of cosmic rays. Using a cloud chamber, a common experimental tool in the early days of particle physics, the cloud chamber supercooled vapor condenses across a line of ions created by the passage of a charged particle. The result is a visible track whose density depends on the particle's speed. When the cloud chamber is placed in a magnetic field, the paths of charged particles are curved. Measurements of the curvature of their trajectories can be used to determine the charge and momentum, and thus the mass of the particles. So that's what you're seeing here. Positrons do not form a part of ordinary matter. They are produced in high energy collisions of charged particles or gamma rays with matter in a process called Pear Production, in which an ordinary electron and a positron are produced simultaneously. electric charge is conserved, but enough energy must be made available to account for the energy equivalent of the rest masses of the particles. So this diagram shows the pair production process for the two photons. You got a photon coming in, and then an electron, both positive and negative, are produced. And you can see where they're going in this particular magnetic field. So when these two particles annihilate, both particles disappear and 2 or 3 gamma ray photons appear with a total energy of 2mc squared. Decay into a single photon is impossible because it won't conserve energy or momentum. Positrons also occur in the decay of some unstable nuclei. Recall that nuclei with too many neutrons for stability often emit a beta minus particle, decreasing n by 1 and increasing z by 1. A nucleus with too few neutrons for stability may respond by converting a proton to a neutron and emitting a positron. So such nucleides don't occur in nature, but they can be produced artificially by neutron bombardment of stable nuclei in nuclear reactors. An example is the unstable odd nuclei of sodium-22, which has 1 fewer neutrons than the stable sodium-23. The nuclide 22 decays with a half-life of 2.6 years by emitting a positron, leaving a stable even nuclei with the same number. A is equal to 22. So in classical physics, we describe the interaction of charged particles in terms of Coulomb's law of forces. In quantum mechanics, we can describe this interaction in terms of the emission and absorption of photons. So 2 electrons repel each other as one emits a photon and the other absorbs it, just as 2 skaters can push each other apart by tossing a ball back and forth between them. If the charges are opposite and the forces are attractive, we imagine the skaters grabbing the ball away from each other. We can say that the electromagnetic interaction between 2 charged particles is mediated or transmitted by those photons. So in 1935, the nature of the nuclear force which binds protons and nucleons together, despite the electrical repulsions of the protons, was a complete mystery. In that year, Japanese physicist Hideki Yukawa proposed a hypothetical particle called a meson, with mass intermediate between those of the electron and the proton. Yukawa suggested that the nucleons could interact by emitting and absorbing mesons in a process analogous to the electrical interaction between charged particles by the exchange of photons. And at that time, there wasn't the slightest shred of evidence that mesons actually existed, but it was clear that a radical idea was needed in order to understand nuclear forces. So some blind alleys were encountered in developing the idea. In 1937, 2 new particles were discovered. They're now known as muons, and they have a charge equal to that of the electron, and its antiparticle has a positive charge of equal magnitude. The 2 particles have equal mass, about 207 times the electron mass. The energy equivalent is about 106 MeV. So the rest mass can be expressed as this. Muons, like electrons, have a spin 1/2. They are unstable. Each decays usually into an electron with the same sign plus 2 neutrinos with a lifetime of about this. In other words, they act very much like massive electrons. And then it became clear that these particles have no strong interactions with nuclei and therefore could not be Yukawa's mesons. So in 1947, yet another family of unstable particles were discovered. They were christened as pions or pi mesons. They have charges plus E, minus E, and 0. The charged pions have masses of about 273 times the electron mass, with rest energy of about 140 MeV. Each usually decays into a muon with the same sign plus a neutrino with a lifetime. It's pretty short. The neutral pion has a smaller mass with corresponding energy of 135 MeV and decays into 2 gamma ray photons. And the pions do interact strongly with nuclei, and they are particles predicted by Yukawa as mediators of the nuclear force. So the discovery of pions in 1947 resolved some questions about the nuclear force, but more surprises loomed on the horizon. And if you go into high energy physics, you get to see more about this. So by 1950, you've got these four forces: strong, weak, strong, electromagnetic, weak, and gravitational. Obviously, gravity and electromagnetism are familiar from classical physics. They both have 1/r² dependence on distance, but the gravitational force is much weaker. So in other words, the gravitational attraction of two protons is smaller than their electrical repulsion by about 10 to the 36. That's pretty big. The gravitational force is of primary importance in the structure of stars and large-scale behavior of the universe, but it doesn't play a significant role in particle interactions. The two other forces are less familiar. Strong interaction is responsible for the nuclear force and also for the reduction of pions and several other particles in high energy collisions. Within its range, the strong interaction is roughly 100 times as strong as the electromagnetic interaction, but it drops off with a distance more quickly than this. The fourth interaction, called the weak interaction, is responsible for beta decay, such as the conversion of a neutron into a proton, electron, and antineutrino. It's also responsible for the decay of many unstable particles. And like the strong interaction, the weak interaction is a short range interaction, but is weaker by about a factor of 10 to the 9, which is why you have strong and weak. So it became useful to classify particles in terms of their interactions. You've got hadrons, which are strong interactions, and leptons, which do not. Hadrons include baryons and mesons. Baryons are nucleons and have more massive particles that resemble nucleons. And you can distinguish between bosons, which have 0 or integer spins, and fermions, which have half integer spins. Fermions obey the exclusion principle and bosons do not. You have several different types of fundamental particles here. They're all kind of generally described here. You've got quarks, you've got, again, your conservation laws here do come into play. The classical conversion laws of energy, momentum, angular momentum, electric charge are believed to be obeyed in all interactions. These are considered to be absolute. Baryon number is also conserved in all interactions, and the decay of strange particles provide conditional conservation laws, ones that are obeyed in some interactions but not in others. There is a concept here called strangeness. These are produced when in higher energy collisions, such as pi plus, proton, and K and the hyperon were always produced together. The frequency of recurrence of the production process suggests that it was a strong interaction process, but the relatively long lifespans of these particles suggest that the decay was a weak interaction. This led physicists to introduce a new quantity called strangeness. So you've got hyperons, which are assigned a strangeness value, and associated mesons were assigned a value of S is equal to 1. The corresponding antiparticles have opposite strangeness. Strangeness is conserved in particle production such as this. The initial strangeness is 1 or -1, and the final strangeness is 0. All observations of these particles are consistent with the conclusion that strangeness is conserved in strong interactions, but that it can change by 0 or 1 in units of weak interactions. You do have different types of particles here. I'm not that concerned with you being able to name all of these. You've got grand unified theories, which are still speculative. The grand unified, in other words, you're trying to unify all of these particular rules into one particular theory. This is a very difficult thing to do, and that is something that is a pursuit of scientists, but I don't know that we're ever going to get there. In order to be able to unify all four fundamental interactions, into a grand unified theory or a theory of everything would be a nice goal. Such theories range from speculative to the fantastic. One popular ingredient is space-time continuum with more than 4 dimensions, containing structures called strings. Another element is supersymmetry, which gives every boson a fermion superpartner. Such concepts lead to the prediction of whole new families of particles, including leptons, photons, quarks, bound together by gluinos, and even winos and WIMPs. Basically, they're trying to figure out exactly what all of the rules are of this, and it's going to take time.